pleasure to introduce Haibin Lin, who works on LLM infrastructure at Bytedance Seed, and before that has done a lot of work on MXNet and Amazon. Today, he'll be talking about Volcano Engine Reinforcement Learning for LLMs, or verl, an extremely popular reinforcement learning pipeline that provides a hybrid controller programming model, first-class support for PPO, GRPO, DAP, and others, and plug-and-play integration with PyTorch. But before I go into too much detail myself, I'll let Haibin take the stage, and I just want to note at the end, a panel of engineers from PyTorch will be here to ask questions as well.
Cool. Thanks, Sahan, for the introduction. So my name is Haibin from Bytedance Seed. So in general, I work on the training infrastructure from pre-training to post-training. And today I'm going to talk about the open source project we are driving for reinforcement learning. So it's called verl. And so let's start with the motivation. So, post-training is becoming more and more important, and where can we see the advancements come from? So there are a few numbers here to show. So from recent upgrades from the models from OpenAI, we can see that the reasoning capabilities jump quite a bit from GPT 4.0 to 0.1. And one of the main differences between these training recipes is that in 0.1, there are significantly more resources poured into the post-training pipeline, doing the test time scaling as well as a compute-heavy reinforcement learning. And we can see the a few related benchmarks on coding and math increase quite a bit in terms of the capability of doing the reasoning on these kind of tasks. And beyond that, we also see that there are a few new models or products released related to agentic tasks. For instance, the deep research capability, as well as operators, and recently OpenAI agent. And it was explicitly told in the blog post where the training was actually using end-to-end reinforcement learning methods to actually allow the model to interact with the real-world tasks, like using these different kind of tools, like the sandboxes and browser. So as we can see, there are, RL is playing more and more important role in the post-training process. So RL is important, but what are the technical challenges when we try to run large-scale RL? And we can see the RL as a data flow. Just don't think about LLM for now. So there are quite a few number of RL algorithms, and we can express them as a data flow graph, where in the data flow graph, in the RL algorithm, there are quite a few differences between reinforcement learning with the traditional pre-training or fine-tuning training paradigm. So there are multiple models involved in the RL training process. So there's the actor, where typically you train the actor to learn some policy, which is the final model you want to use after the training. There's also the critic model, where usually give some value estimate on the current state of the trajectory and action you take. There's the reference model that is more related to LLMs, where we typically want to have some reference model, usually the pre-trained base model, so that the model you are updating, the final policy, is not that different, that far away from the original reference model, so that the model you have optimized for is still talking in English or human language, so that they are not too much different. And of course, there's the reward model, which is quite important because you may have a few models that mix different reward signals together, so that it provides the right signal for the model to learn the right policy. And as we can see, from different from the algorithm perspective, people may choose whether to use critic or not, and there are different choices in designing the algorithm. And Of course, from the pipeline perspective, there are a few stages when we chain all these different models together. So there are internal dependencies between different models, and from the system perspective, we need to consider all these data dependency when we implement the correct version of the algorithm. And the other hand, on the system perspective, there are indeed a lot of different kind of workloads together, in this single training run. So, in the typically there will be a generation phase where we take the original model and we use the model to generate, in LLM world, you take a prompt and then you generate the responses. We take that as the training trajectory, which is used later for training. We of course also run inference with different models, usually with the reference model, so that we can have some kind of reference score. And finally, we use the generated training trajectories and use that as the training samples to perform the policy updates to update the parameters. And what's more special is that the updated model is then completing a full loop, like use that model weights to do the generation and inference and training for the next iteration. So you can see that typically in the synchronous training algorithms, there will be some dependencies where you use the same model weights first for generation and then use for training and so on. So if we take the RL data flow and put that in the context of LLMs, it becomes more complex. So in the world of LLMs, it's quite crucial that we need to have a large cluster to hold all the model shards. And from this graph, we can see that basically each operator in this data flow graph can become a quite complex, huge distributed computing workflow, where the actor can be a MOE model with billions of parameters, and that requires ND parallelism, multiple processes to compute the actual value of either during training or during the generation. And of course, the constraint still holds because we want to follow the dependency between different nodes. So the main challenge is how do we express this kind of algorithm in a more flexible way, because different roles can be plugged in and changed depending on the need of the algorithm. On the other hand, we also want to make it as efficient as possible by leveraging existing training or inference components available out there. So that's the motivation for building verl, and how is verl good for this kind of workload. So I will break it down into a few slides. So in overall, we want to have a both flexible and efficient framework for RL. So on the flexibility side, so basically we want to have a single controller programming experience. So basically, the idea of the single controller is that we want the control logic to happen on a single process, right? So it is the best for scientists to write, or it is easiest if you can write a single-threaded program that express all these different kind of control logic. And in the context of RL, because there are generation phase, computing different kind of values, log probabilities. If we can just have a single-thread program by training all these logic together, that would be the best for flexibility. So on this figure here, you can basically see some draft pseudocode for what a training loop in verl look like. So it's very intuitive. And with the introduction of this single controller programming experience, then we can easily express different kind of our algorithms like PPO, GRPO, GSPO, and so on. Okay, so On the other hand, we also want the training framework to be as efficient as possible. And usually the efficiency comes from the multi-controller paradigm, which I will explain a little bit more later in a few slides. But basically, what we want is a set of existing technologies that we can leverage to accelerate the training and generation phase of the LLMs. And usually, if we take a look at FSDB2 or VLM, they involve different kind of parallelisms, and multi-controller is used as a paradigm to accelerate the tensor parallel or data parallel process, where the context of multi-controller means that each the controller logic runs on different processes, and they drive the computing control logic together in concurrently to achieve the fastest performance. So let's hold this for quite a few minutes, and I will come back to this in more details on how we combine these two. And a few more words about the efficiency of the verl framework is that we initially started with a hybrid engine design, which is designed for synchronous RL. For synchronous RL, basically we co-locate all these different models on the same set of machines, and we provide some context switching mechanism to either offload or reload the model we want to use to fully utilize all the GPU memory as well as compute resources we have. And because we have different optimal parallelism strategies for different kind of phases, for generation and for training, they may require different parallelism strategy. So we provide a sharding mechanism to shard the model weights to the right one so that they achieve the best optimal parallelism strategy. And in particular, so we designed the hybrid engine in a way that the training process and the generation process with the VLM specifically are in the same one, so they can share the same memory space and reduce memory fragmentation. So these are the few characteristics we have for the verl project, and so far we have gained quite significant impact in the open source community. We have around 12K stars, a lot of works, and a lot of contributors from the community up to 1.5K PRs, and we are really serious about reviewing the contributions. Although we have a very limited bandwidth, but we try to have a vibrant community for everyone to contribute. And apart from the things I talked about, there are other capabilities in the repository. For instance, multimodal training, large-scale MOE for really serious users, and also for users from the academia. We also provide low resources solutions like multi-GPU LoRa, and also the capability to interact with different kind of sandboxes and tools. And most importantly, I think it's very important for the training framework to provide reproducible training recipes. And in our repository, we have provided a few, for instance, the DAPO recipe, and also the retool recipe that is used for agentic RL training. So I want to dive a little deeper into the programming paradigm behind verl, and the original paper is called Hyperflow that we published in Eurosys. So let's go back to the concept of the single controller and multi-controller a bit more. So basically, in the single controller programming paradigm, we have one process doing all the controlling logic. So this centralized controller basically manages all the computing resources and dispatch the computing operations that's run on different processes. So basically here, this is a graph taken from pathways where this controller will communicate with all these different hosts and devices and dispatches the corresponding computation or movement operation to these workers. So it is easiest to write because there's only one central controller, but there may be communication overhead when the scale is large. And in contrary, there's the multi-controller paradigm where each worker has its own controller. So each worker has its own process that has the control logic, so that when we run the program, it's basically the same program, but each process receives different portion of the data, and they concurrently run together and achieve the result. And they launch the communication and computation kernels concurrently. So this would help avoid the bottleneck of the single controller when the number of processes is large. However, it's much more difficult to program because each worker has its own control logic, and it becomes more complicated when you have multiple models and roles in the same program. And whenever it involves sending data across different workers, considering different algorithms, that can be really complicated because basically in this single program, you have to consider all the different kind of interactions, communications between different models and roles in the same world. So we try to handle this kind of dilemma is the introduction of hybrid controller, where we have a single controller controlling the operators shown in this graph, and this is mostly for the inter-operator control logic. But as I said, each operator here actually correspond to a giant compute mesh. And to achieve the best efficiency inside each operator, then it's managed by multiple controllers. In this specific context, for instance, we use Megatron or FSDP for achieving the best training controlling logic inside training engine. So basically, the single controller manages multiple controllers to process the data flow. So that strikes some balance between usability and the efficiency. So what it looks like in code, so it's something like this. So as we said on the left, there will be one single process that's driving the control logic of the data flow graph. And inside each operator, for instance, here we have the critical compute values that happens on a mesh of processes. So basically, we have a few primitives in verl that helps register, the communication pattern between the single controller and the multi-controller mesh to dispatch the corresponding data and collect the results when such communication happens. So on the right-hand side, so we basically define the computing logic for the critic that happens in the SPMD fashion, where multiple processes are driving the computation for the critic model together. So what we actually have is basically some kind of RPC mechanism where the single controller sends to a group of multiple controllers, and we leverage the register decorator to enhance this kind of dispatch and collect behavior. Okay. And in the next slide, so basically I mentioned that the one unique piece in the our training program is that we have different kind of computing workload, where there's the training phase and generation phase, and we use the updated model weights from training, and then use that weights again for generation. So there will be some sequential dependencies, and it's very important to transfer the weights and do the corresponding resharding to achieve the best optimal layout for different stages. So in verl, basically, here's some example of how or details about how verl tries to achieve optimal sharding with different phases. And in general, we are providing a general purpose implementation that can be further optimized. For instance, here we have the training process with a larger TP domain, but for generation phase, the TP domain size is reduced from 4 to 2, right? So basically, in our implementation, we use the D-tensor abstraction to express the model weights, and then basically we leverage nickel plus RDMA or InfiniBand to do the communication when we perform the resharding. And basically the pseudocode is shown here in the box below. And it's very important to do this kind of resharding and transfer in the final grain, because sometimes model can be really large in terms of number of parameters, and in practice we implement that in a per tensor or some kind of bucket-based solution to do the communication transfers to avoid LLMs. Okay, so that's the main idea or the main technologies behind verl, and recently there are more and more interest in approaching RL training for agentic tasks. And here there's one example of how an actual RL training with the sandbox interaction looks like, where the model will take a prompt and then generate the response that is a mixture of text and code, and we want to actually send the code to some code sandbox environment and get the feedback from the interpreter, be it the status of the unit test or whether the compilation failed, signals like that. So there will be some new requirements to support this kind of agentic RL training. So specifically, basically here we have more complex interactions during the rollout phase, basically the generation phase, when we interact with the environment. And what it looks like in the timeline is something I showed here. So initially we have a synchronous rollout engine. The rollout is basically meant for doing LLM generation and gather the trajectory. And in the initial synchronous version, there's some synchronization problems with different kind of samples and how they interact with the environments. Basically, it's bottlenecked by the slowest one in the batch. So the synchronous engine operate on the batch level, and there will be bubbles or idle time during the rollout phase. And later we introduce an asynchronous rollout server that basically kind of reuses what is available in the VLM serving engine, VLM server that handles each request in a streaming fashion, and each request can have its own timing logic in when to stop the generation and when to interact with the environment, so that all different kind of requests can utilize the computing resources in a more efficient manner. So doing the generation and asynchronous server is very important when we have complex rollout behavior. So basically here, each request may interact with the environment multiple times. It's not consistent across different requests. On the other hand, the generated sentence may have variable length. So the behavior between different samples can be quite different. Okay, so with that, so how do we actually implement something that is doing the tool calling during the generation? So here's one demo code that we recently introduced to verl. So basically here we program based on a per sample basis. So the interface here is you're given a prompt, basically a message, and then the user can basically leverage the generate API that is under the hood calling to VLLM or Echelon servers to do the LLM generation. And the user have the flexibility to handle what kind of tool it wants to call, and also do the corresponding generation for the token masks, and performing this kind of different kind of complex tool settings. So that's what it looks like in implementing some new agent training loop in verl. And so furthermore, we made this kind of improvement in the verl agent loop implementation. Basically, we have the inference engine and agent loop decoupled. So the generate API would either call the LLM implementation or Echelon implementation. It can be swapped based on your preference. And the parallel async loop is running asynchronously for each request, and it's relatively easy to have different kind of policies to load balance different requests or collocate them based on your preference. But you can modify the code for that. And furthermore, we provide a reproducible training recipe for the retool paper, which achieves a reasonable, actually a little bit better score with the 32B model compared to the paper. Okay, and so there are 2 or 3 more slides I want to show to elaborate more on some of the recent updates with verl. And one is to support huge MOE models, and it's becoming a clear trend in the open source community to have large MOE models that is more efficient in terms of the system performance versus accuracy trade-off. So in the earlier releases, we have released the DeepSeek integration with the MOE back implementation in Megatron that is runnable in 256 H100 GPUs with 0.12 MFU. I think this can be improved further, and we're shooting for 0.15 or 0.20 with the latest version of Megatron. And so in practice here, we use BF16 for tensor parallel inference. That is actually happening in multiple nodes, and we are working on doing some quantization in the generation phase so that the inference can happen in one node instead of multiple nodes to improve the performance. And the recipe has been verified by some members from the community that the reward curve looks normal. So you can also look for more details and follow up in the issue here. Okay. And there's some other interest in having some kind of asynchronous training pipeline for reinforcement learning in general. There are actually some frameworks are dedicating just to design some asynchronous RL pipeline. So in this slide, I want to explain the differences between the choice of different kind of architecture and how people place different kind of roles in the cluster. So on the right-hand side in the graph A, so this is a disaggregated architecture. So some notable examples are, for instance, TRL, where the training and generation devices are placed on different devices, and this is relatively easy to integrate with the existing component, but it may be problematic when there's a switch between different roles, and there will be bubbles or idle time because of the algorithm itself, or if it is a synchronous one. And the second graph here, B, is the implementation in verl. A and B are both for the synchronous training, right? So in verl, all models are co-located together on the same set of machines, and we use the parameter onload and offload to switch the context between training and generation and perform the resharding. So this is okay for a synchronous training scenario, but it introduced some of the context switch overhead. And what was proposed is that actually with the disaggregated device placement, there are some benefits because there's no context switch, right? So you don't have to move parameters from GPU and to CPU, and this is especially important if you have very large number of models, and each model has large number of parameters, right? For instance, if you train Kimi K2 with 1 trillion parameters, the co-located architecture may experience CPU auto memory, like issues like that. So with models of that scale, the disaggregated architecture is a must. But how do we try to improve the efficiency of the disaggregated architecture? Then there are some proposals like one step of asynchronous training pipeline, where we can allow some of the staleness in the model weights when doing the generation and training. So basically, the generation model parameter is one step stale from the previous step, basically. And we use the stale ways to generate the trajectory, and then use that for training, so that you can fill in the bubble in the device mesh and form a pipeline based on that. And to implement what was described in the graph C, that is the one-step asynchronous training pipeline, it's relatively easy for verl to implement that because we have the hybrid controller. You can implement the control logic in a single program, and you can choose which set of machines to do what. So we have implemented the async one step of pipeline in verl in this recipe highlighted in the underscored notes here. And in general, we did some benchmark, and it's actually contributed by a community member, and it's like 20% or more speed up compared to the synchronous training pipeline. And we have some more efforts in introducing the fully asynchronous pipeline, because in this case, there are still problems with the async one step of pipeline, where there may be some long tail problems in the if the staleness of the model weight is fixed. For instance, you may encounter one very hard example in a prompt in a batch, and that single generation may take really long, right? So this is not solved in the one step of asynchronous training pipeline. Okay, so finally, here's the last slide I have to share a bit more about the roadmap of the verl project. So one thing we're looking at is to have a more modular design, where we want to have algorithm agnostic training engine abstractions, so that they purely focus on how to compute certain losses and all. Currently, in the older version of verl, it's still kind of interleaved with different kind of PPO or RL algorithms, and we want to have a better abstraction to separate them away. And of course, as I mentioned, we want to have more asynchronous, more efficient training pipeline. And this has been mentioned in a few papers already. And specifically, for instance, we want to have an async partial rollout where each sample can have a different number of model weights together. For instance, you generate to a certain length and you update the weights because of this is not done yet, and then you update the generator model weights again, and that can be happening in a few iterations until you generate the longest sequence. So basically, the training is not waiting for this longest generation sequence to complete, but this way, you have more stillness in the trajectory, but you can fill in all this compute idleness in the cluster. And you probably need to do some important sampling or some tuning in the algorithm to avoid losing the accuracy. And besides that, we are working with the community to improve the rollout performance, such as IP8 and other kind of parallelisms. And we are working on more recipes to reproduce more papers for some of the important tasks like SWE bench. And you can see the issue tracker here on the GitHub with a list of efforts that is ongoing, and we are constantly updating the GitHub issue here. And we welcome everyone to try it out and contribute back to the community. And you can join our Slack channel with the QR code here. And yeah, that's it. Thanks for listening.
Yeah, thank you. And I guess now we'll leave it to the panel to ask some questions. Oh, I guess the first question is how efficient is weight transfer implementation in verl, or is there room for improvement?
Right. So as I mentioned, so we have a kind of very general implementation for the weight transfer that I showed a few slides ago. So there are actually some optimization you can do for where is it? Actually, I'm not sure where the slide is. So here.
Yeah, the slides are not shared anymore. So.
Oh, okay. Sorry.
It's back. It's back now.
Yeah. So basically, we do the weight transfer on a per parameter basis, and we first all gather the full weights for that single parameter, and then load it to VLM, right? Because in VLM, the current API assumes a full tensor is provided to VLM, and if the VLM performs tensor parallel, there are actually some weights being discarded and not used anymore. So there will be some wasted communication in this implementation, and we are actually working with the VLM team to explore some more efficient weight loading APIs. So in the past, we have been using older version of VLM, and we just provide some patches so that we can avoid this kind of redundant communication. But in general, I think the weight loading overhead is relatively small, especially in the agentic RL training workload where the generation phase can actually take quite long. And in the paper, we actually have implemented some per model based optimized weight resharding implementation, but those are not general enough. So later we just stopped maintaining that, and we're actually happy to come back to a more efficient implementation if it is more general and easy to maintain.
Yeah, I guess the next question is, the current implementation relies heavily on Ray. What is the consideration for the Ray dependency? Is there a plan to use like a simpler non-Ray implementation for users not familiar with Ray?
Yeah, I think it's a pretty good question. So from verl's perspective, we leverage whatever off the shelf is useful for verl, and what we actually really need is some kind of Pythonic RPC distributed computing engine that we can dispatch all these kind of data to different set of multi-controller groups. What Ray provide certainly includes the RPC mechanism, but from verl's perspective, we probably don't need the resource scheduling and resource management aspect of the Ray project. So I think a more lightweight distributed computing engine would help, although I don't think we have an alternative right now. We do have one alternative implementation that uses Torch RPC, but Torch RPC is kind of not really maintained by Upstream, so that was never merged. But in general, we're happy to work with the community to provide better experience if there's other better option. But I think on the other hand, I think Ray itself is relatively easy to get started. It has very good documentation, and it's very Pythonic. So, yeah, I think it's okay so far.
Yeah, and then the next question is like, many agent frameworks use OpenAI chat completion APIs. For example, Agent RL. Why do you think token in, token out is preferred way instead of using the chat completion API?
Yeah, very good question. So we do have some chat completion based implementation in verl, and we did find some problem with this implementation because with a chat completion API, basically you have the text as the input and output. And usually what people do with the agentic RL is there are multiple turns involved when generating the sequence. So basically what you're actually doing is concatenating the generated text with some more text results, and then use that for the next round of generation. And what we found is that this kind of behavior of concatenating the text may introduce some inconsistency when you encode and decode the same set of text again. So instead, we use the token IDs directly from the generation API. So this will help avoid some inconsistency between training and generation, and that improve the score of the or the actual outcome of the training policy better. Yeah, so basically we found some discrepancy between encoding and decoding again using the same set of text. So that is very important for RL to maintain the kind of consistency between the rollout and training.
If
or
I could ask
the actual use. What?
Oh, sorry. If I could ask a quick follow-up on this related to like, the issue you described is something that you found when you're just kind of testing things out. But when you support a library like verl that is the backbone for a lot of people doing some really cool stuff, like how do you handle testing when testing now involves using large LLMs as part of your training loop?
Yeah, that's a very good question. So, I mean, we adopt some of the regular software engineering practices. We have a unit test that if those can be run on CPU, we leverage CPU as much as possible. And for LLMs, we usually do some sanity test on small model weights, for instance, like models with a 0.5b parameters. And for some of the important end-to-end recipes, we have like end-to-end tests that we launch every day to verify the training curves. But it's true that it's very hard to do regression tests for all these kind of different use cases, on a very high frequency, and we do have some kind of priority in terms of like which set of tests are important, and we have more resources to test them. And we heavily rely on the feedback from the community as well. There are bugs reported by the GitHub issues and from the Slack chat. So we will take a look when things like serious regression happens.
How do you see the role of SFT changing with the rise of more and more post-training RL things?
Yeah, it's a very good question. Yeah, I think SFT is still useful when you have a set of prompt and label responses. That is a quick way to boost the performance of model capability in a certain area. But with what we see is there are like more and more computing resources dedicated for the RL phase, and especially you can do test time compute, and you can design some kind of verifier that is more specific to a certain domain and ask the model to explore more. So in general, it's possible to get a more general purpose that with the verifier with RL, and you can potentially uncover more capabilities if the verifier or the reward model provides the right signal. So I guess the question depends on the cost of labeling for SFT versus how easy it is to have a nice constructed verifier or a reward signal you can provide to RL. If it is easier to provide a reward signal, then RL is something that is more scalable. You just put more compute and let the model explore itself and learn the right alignment between what you want to optimize in the reward versus the actual policy you want to train.
Yeah. Another question is, what's the maximum context size you can train with verl? You also do Visa. Yeah.
Yeah, it's a good question. I don't think we have a specific benchmark for the largest context size, but in general, we have the Megatron backend where the context parallel size is an option you can feed into Megatron. So you can certainly run context parallel with verl, and it usually also depends on the number of GPUs you have, and the type of the memory of each GPU you have. And so there are some known issues in the verl code base where if you don't enable the remove padding optimization in verl, you may end up with padding a lot of sequences to the same max length. So that's something you want to avoid. And in practice, we see some of the community forks where people achieved like 64K or something in training long context models, but we don't have like very official benchmarks in the max sequence length for specific model sizes with a specific cluster size so far. Yeah.
Is visual LLM support working in verl? How about other modalities?
Okay. Visual, I assume this is like visual language models.
Yeah.
Yeah, we do support visual language models. So currently there are images and video support if we're talking about visual signals, and we have that in our data set, and we have some examples with Queen VL models like that. I think in general we do have some framework management problem with integrating more VL models, VL based models in verl, because I think that the way people try to design their VL model interface is different. For instance, Gemma 3 has certain way of doing the image encoding. So even though they are all in the Hugging Face library, the way they organize their model and their config is a bit different. So for verl, if we actually try to enable all these model training in the main branch, that means there will be a lot of like model specific branches in order to actually call the right encoder. So that's a challenge we have, and but in general we do want to have better like multi-model support. In terms of other modalities other than images and videos, we do have a ongoing PR with audio support. So there will be some speech data sets, and people try to apply RL on that to improve the capability of the model in certain area. And yeah, we're working on trying to get that merged, but it's not yet available in the main branch yet.
And is that audio in or audio out or both?
I think audio in. And actually, for the output side, I know there are members from the community working on unified image generation models, like the Bagel model, to improve the image generation capability with the transformer backbone. On those kind of models, I think one of the bottleneck is there are not very good inference library support for image generation models, because I think it requires some more changes in VLM or SGLang to actually have more very efficient implementation. So I think that's more of a community effort to enable this kind of image generation models as well.
So Colin Taylor, an engineer on PyTorch, also was asking, how are you using RDMA for weight transfer from trainer to VLLM? Are you using IB verbs directly?
So from the framework perspective, we basically just call nickel, just torch distributed, all gather things like that. And nickel basically detects whether there's RDMA or IB support on the hood based on the availability of the hardware. And in terms of the weight transfer, we have a few different implementations for VLM. We have especially for the co-location phase. So VLM worker process and the FSDP trainer live in the same process. So basically, it's like any normal PyTorch program, right? So you just do some communication with the torch distributed, then the weight resharding is done. And there are some more other variants like SGLang where they have a separate process. So there will be like inter-process communication done to transfer the weight from the training processes to the inferences workers. Yeah, but basically, those are all heavily based on nickel right now. And I think we initially explored using Ray objects to do the communication, but those are not really friendly to GPUs, cannot do like GPU direct RDMAs. So that prototype was discarded. But we know that the Ray community is also working hard to enable GPU-based object stores to directly transfer GPUs with the Ray APIs, GPU objects with Ray APIs. And we actually look forward to have that kind of feature available in verl as well.
Oh, I guess we can move on for a little bit. So also, what was the most difficult aspect of debugging RL training runs? Yeah.
Yeah, it's very good question. I think, yeah, so RL itself can be quite unstable if you don't train it right. For instance, the reward and the entropy, fluctuates. And we actually build quite some of the tools, try to understand whether there's some discrepancy of the numerics between the training and generation. For instance, the log probabilities from generation, whether it's different from the one produced by training, things like that. And we found it very important to have some kind of visualization or some kind of dumping the generated output to have some kind of visual view to see the vibe of what's the generated sample, whether it is not following the format or it is actually reasoning in the wrong direction, things like that, to know whether the models is lacking certain capability or we just didn't have the right algorithm. So I guess it's a mixture of many things, and we found that it's very important to have unit tests for every individual components, like for the training process and for the generation process, and test whether it produces the right output. And there are also cases like training with very large models and see whether certain components fail or produce different or incorrect results with some of the irregular runs. And I think in general it's a hard problem because you have to make sure the system is right and then debug the algorithm.
Okay. Oh, sorry. I guess to follow up on like the question we asked before about RDMAs, if you are using nickel for RDMA weight transfer, we have separate multi-controller actor groups sharing the same process in that group setup. Are these RDMA transfers managed by a single controller?
No, they're not managed by a single controller. Yeah, so we did have to set up special process groups between these different roles. So as I said, like we initially tried to do that via the single controller, but it is heavily reliant on the Ray, and with Ray, the GPU tensor performance is not great, and also there will be some single controller bottleneck if all the traffic goes to a single controller and then goes to the corresponding roles. So it's more like the single controller send a signal asking for all the corresponding worker groups to start a communication, and in practice we did set up dedicated process groups just for weight transfer because otherwise it will be too slow.
Yeah, and I think we just have like one more question left.
Mhm.
Yeah. Yeah. So you recently landed a one-step off async training recipe. Can you say a bit about some of the technical challenges there? So like resource management, parameter sync, all that stuff, as well as your future work and like what you're considering doing there.
Yeah. So yeah, with resource management, I think it's relatively fine because with Ray and the single controller interface, it's relatively easy to have a different kind of resource setup and bind the resources to each kind of the worker groups. Although it may be more involved if you want to do more elasticity in terms of different kind of GPUs go to different kind of roles. And yeah, for parameter sync, it is a bit different compared to the co-located phase because we are syncing between two different set of worker groups, and we would set up a communication process group just for the with sync. And I think in general the challenges are they're on system side as well as on the algorithm side, right? So from the algorithm side, you definitely don't want to have too much staleness in the model weights. So currently it's one step off is usually fine, and there are tricks like important sampling you can play with to try to mitigate the effect of asynchronous model staleness in the model training. And furthermore, I think going forward, like we don't want to stop just at one step off asynchronous pipeline. To more fully utilize the training resources, we actually want a more flexible way of fully async training pipeline, where the model weights can be k step off, and the number of k can be different for different training requests, right? And so as I said, like there are ongoing efforts to make the generation or the LLM server kind of interruptible during training, actually doing inference, so that when we generate the sequence halfway, and then if there's an event of model weight updates, we can apply the updates and continue training. Continue generation for the rest of the decoding steps. So that's something we're still working on, and but I think the main idea is that you want to try to fully utilize the generation resources and co-design some of the staleness aware algorithms so that you don't lose a lot of accuracy when you train these kind of async recipes.
I actually have a follow-up to that question. So it's kind of related to the previous question about debugging RL runs. Like, I imagine this will make things strictly more challenging. Like, are there certain is there certain tooling or instrumentation that you guys are thinking about for debugging these? And is it something that you would provide in verl?
Yeah. So we do have some tools described in our README, in our documentation. So basically, you can dump the generated samples at each stage. So you can have you can know that during generation what kind of sample is generated, and you can take a look. And we also provide some kind of metrics like logging the log probability differences between generation and training. If they are off by quite a lot, that usually means there's something off. Things like that.
Yeah, I guess if there's no more follow-ups to that, thank you so much, Haibin, for the time and the great presentation, and thanks for the folks on the panel here for asking questions and supporting. Yeah, and this video, if you want to watch it again or ask more questions, will be available on Twitter and YouTube as well as LinkedIn as well. Thank you.
Thank you. Thanks for organizing.
Yeah, of course.
Thank you.
Thanks for the great presentation.
Thank
See ya.